Welcome, everyone. Thank you for joining us for today's webinar, A Performance-Based Approach to Fire and Gas Detector Mapping and Why It Matters, presented by Murtaza Gandhi. My name is Naomi, and before I introduce our presenter, I want to go over a few housekeeping items. First, if you have any questions during the webinar, please type them into the Q&A box in your WebEx control panel. With the time remaining at the end of the presentation, our presenter will respond to the questions. Second, this webinar is being recorded and will be posted to the Baker Risk website for future viewing. Finally, at the close of our webinar today, you will be prompted to complete a short survey. We ask and appreciate that you answer it and appreciate your feedback. That concludes the housekeeping items. Now let me introduce today's presenter, Murtaza Gandhi, who manages fire and gas systems mapping and hazardous area classification services at Baker Risk. He has 15 plus years of experience in the process industry with 10 plus years in the field of fire and gas detectors. Also, extensive experience with various phases of the ISA 84 or IEC 61511 functional safety lifecycle, and is a continuous member and leader of ISA at the student, local, and international level since 2001. Now, without further ado, I will turn the time over to Murtaza Gandhi.
Naomi, thanks very much for the introduction. Good morning to everyone in the US and good day to the folks around the world. Thanks for joining today. The presentation topic we have on hand is a performance-based approach to fire and gas detection mapping, and why is it important? So before I start, let me briefly introduce Baker Risk. Baker Risk is a 35-plus-year-old company that deals with a mission to manage hazards through high-value services, products, and research. Our key areas of work are incident investigation and litigation support, in which we conduct accident root cause analysis and evidence collection. In the loss prevention service area, we are looking to prevent and minimize personal and property losses, and fire protection, fire hazard mitigation analysis, fire and gas detection studies like the one that we're going to cover today, hazardous area classification, and others come under this category. Under testing and research and development, we have two major test sites in Texas where we perform numerous tests on structural analysis via shock tube, dispersion and jet fire analysis, and explosion testing. Under the risk management and mitigation services, we perform siting studies, both consequence and risk-based, process hazard analysis, structural upgrades, and blast analysis and protection services. And then finally, in the Baker Risk Learning Center, we provide in-person and online classes on the subjects of Baker Risk's expertise. You can check that out on the bakerrisk.com website. So to today's presentation, the four key takeaways that I want you to take from this presentation. Number one is scenario coverage approach, and I'll define that briefly. But the importance of having consequence-based fire and gas detection mapping is very crucial in the field of performance-based gas detection systems. The second point of interest is risk-based prioritization of detectors. Here we are looking at how you can use the criteria of risk to prioritize which detectors you need to place right now versus what can wait for a year or two. Importance of validating models with testing. It's extremely important to understand the assumptions that goes behind these studies and how these coverage values are calculated. So it's very important to test these models and understand the outcomes of that. And then finally, we will talk about gas detection mapping for a toxic shelter. So based on this, the outline of today's presentation will start with a brief background on mapping. We'll talk about consequence and risk-based approach. That's the methodology we will discuss. We'll discuss the research that Baker Risk has conducted on scenario coverage. and then finally we'll talk and finish with the gas detection on toxic shelters. So the question that we're trying to answer today, why is fire and gas detection study important and how to conduct it? In any processing facility, the whole idea is to produce whatever you're manufacturing in a safe manner that protects your personnel as well as your assets. And the means of doing that is through ensuring that the product, the hazardous product that you may have, stays within the pipe, the vessel, exchanger, or basically no breach or no loss of containment. But as we all know as an industry, loss of containment events happen time to time, and we have to plan for that. The first line of defense is how do you detect if a loss of containment event occurs? And that's going to be the topic of interest. We will also touch on some of the response and how it's important to ensure that when you detect, what actions you take based on it are as crucial as the detection itself. In addition, what has happened recently in the industry with a movement of personnel outside the process areas to ensure their safety, there is less visual and knowledge about what is happening in the field, whether there is a leak, whether there is a small fire, and it takes time to detect all that if personnel are not on their operator rounds, the staff is low, and if they are, then they are sitting in a control room maybe 1,000 feet or 2,000 feet away. So in all those cases, the fire and gas detection system facilitates a prompt mitigation response and gives you that initial visual of what is happening in the field. Now, the question is, how do you decide which detectors to choose? So you have gas detectors, fire, acoustics, and others. The questions that come up generally are, how many detectors do I need? Where to locate them? And then what type of detectors do I need? The idea of consequence and risk has been in place for many, many decades. And we want to try to leverage the information that your site has generated over a number of years through consequence modeling and risk calculations and help do the detector placement with the knowledge of the hazards. So a brief background on what's happening in the industry. Why is it so hard to perform these studies? HAC has said that based on 8 years of offshore data, 60% of the known releases were detected. Now this number is slightly old, and maybe with the advent of technology that we have and the knowledge of gas detection and fire detection that has increased over the years, this number has probably seen a little bit of an uptick. But even then, you would not expect significantly high number of releases still being detected. And the challenge there is not that we don't have the correct intention. It's just the questions like, do we have the detector at the correct location or not? So a few standards have tried to answer that question. There is an API publication 2031, IEC 60079, ISA Technical Report 7 under the S84 standard. And then most clients do have internal standards based on the above or some of their own internal experiences. The traditional studies were pretty much done based on experience. So if you knew about a release at a certain location, you wanted to detect it and you would place the detector there. On the other end of the spectrum is the CFD modeling. And there are instances where CFD modeling is very beneficial, like if you take an example of a room with a compressor, a hydrogen compressor, and you're trying to detect and shut down to make sure that there is not a hydrogen blast scenario due to hydrogen accumulation inside that compressor shed. And in those cases, CFD modeling can be very beneficial. But most scenarios are somewhere in between. And that's where the idea of a consequence-based analysis and risk-based analysis comes into play. So let's get a couple of definitions. ISA Technical Report 84007. And for those who are maybe not familiar, but S84 or ISA 84, IEC 61511 is the standard for safety instrumented systems. And the first version came out in 1996, and the latest version came out a couple years ago. And under that umbrella of the S84 standard, there are multiple technical reports. One of them, which is the Technical Report 7, focuses on fire and gas detection. And it defines two types of coverages. Coverage meaning how well your detectors are covering what you want to cover, right? So in geographic coverage, as the name suggests, you are concerned about the fraction of the geometric area or volume of a monitored process area. So whatever hazard or whatever area or volume you're trying to cover, if a hazard was to occur in that particular location, would your detector be able to detect it or not? And in that particular voting arrangement. So you may have 1 out of 2, 2 out of 2 voting, 2 out of n voting. In all those scenarios, is your detector successfully able to detect and send a signal to your control system? So in other words, simplistically, it's the percentage of area that's covered. The other aspect of coverage, or the other method of coverage, is a scenario coverage. And it is defined as the fraction of the hazard scenarios from the process equipment that's within, again, that same defined or monitored process area that can be detected, considering the likelihood of a release occurring from there. So now we are focusing on the type of the hazard and the likelihood of the hazard depending on the defined voting arrangement. So in other words, you're talking about the percentage of scenarios that can be detected is what defines scenario coverage. Our focus is going to be on scenario coverage for today's presentation, and we'll touch various aspects of it. So how is Baker Risk doing this? Baker Risk assists our clients in the placement and optimization of detectors. And we've created a proprietary software called Fire and Gas Tool, or F&G tool, that looks at and does the placement and coverage in a 3D environment. We are able to import the consequence and risk results from the consequence and risk software. For Baker Risk, that's SafeSite. And then we optimize the detectors and give you a detector coverage value, and then the steps following that. So let's talk about the methodology, both the consequence-based and the risk-based approach. So this is a typical workflow of a fire and gas mapping study. The first and the most important thing is also the most crucial thing in terms of defining whether you have a successful project or not. And that is defining the performance criteria. It's very important at the early stages to realize what you're trying to achieve from your fire and gas system. Is it to cover a location that's extremely remote and there are no people out there, and you want eyes and ears over there and you want very quick detection? Or is it where this is a supplemental system in addition to other leak detection systems? Whether you will alarm based on it, whether you will initiate a shutdown, or whether any type of venting action needs to begin, or worst, if there is an evacuation that needs to occur based on this. And all those things help define what set points you will need for your alarms, and then what actions you will take based on those different set points. So once you have a performance criteria that's defined, accepted, and agreed to, then you start with the next step of defining or designing the model. And you can use the information from your CAD drawings. You can import from 3D softwares in STL or AutoCAD 3D type models. But based on the P&ID reviews and the CAD drawings, you prepare a preliminary model of the facility. Once that is done, the existing consequence or risk models are imported into the software. For sites that Baker Risk has conducted siting studies and it's done in safe site, our software fire and gas tool is able to connect with that directly. But for sites that we've not done, either we are able to replicate what we need in terms of based on the inputs that you may have already generated for your risk-based studies, or we can take the outputs and replicate it to import and generate the results that we need for fire and gas mapping. After that is done, a site visit is conducted to verify the 3D model is correct, and the 3D model development is completed after that. Then begins the iterative process of detector layout, generation, and then optimization. So first pass detector layout is put in during the site visit, and if it's for a greenfield facility, it's based on 3D models like Navisworks and others. And then when we go to the site, it's important to, again, make sure that you've studied the hazard and you know where the gas clouds are going, so you can do your first pass detection that covers as many scenarios as possible. And then when you, once the site visit is completed, that's when the optimization is conducted and you define what number of detectors you're going to end up with. Prioritization of detectors is conducted if needed, and then you generate a report finally. There are numerous types of fire and gas detectors out there. There are point gas detectors, line detectors or open part detectors, acoustic detectors. There are fire detectors like conical flame, UV, IR types. There are heat detectors and also fusible plugs and others. The key thing to take away from this slide is that there is not one thing that will cover the entire site. There may be camera-based systems too. It's all a combination. So the whole purpose of this analysis is to understand what you're trying to cover and what is the best solution to cover it. And that is going to be a combination of some or all of these different technologies out there. So this is an example. The 3D model is built with plot plan and site visit data. The vessels, buildings, structures, pipe rack, etc. And then the flammable, toxic, and fire scenarios are imported from the consequence models. And then finally, detector locations are optimized and the coverage calculated as per the risk calculations. So this is a 3D view of a facility with gas detection, fire or flame detection, and then also toxic detection. So as you can see, the vessels are shown in green, the structures, there are pipe racks, and then there are buildings. But the blue dots with the circle around it are the flammable gas detectors. The conical flame detectors are shown, and then there are certain toxic detectors that are shown in pink in the background here as well. Next couple of slides, I'll show an example facility that we've analyzed. So we looked at the plot plan of the unit, we did a physical survey, and we developed a 3D model before we went to the site, and then we completed the model once we went to the site and found any changes or discrepancies that we needed to cover. So you can see that this is, on the top is the process facility, and just south of that, or at the bottom, is the residential campsite. This particular facility is in a very remote location and hence needs personnel to live out there for significant periods of time. This makes the detection analysis extremely crucial because the lives of a lot of people are immediately at risk in case of a release. And hence, the site was very cognizant of the hazards, and they wanted us to do as much as we could in terms of voting mechanisms, in terms of coverage, to prevent two things: to prevent, of course, a safety hazard, but also to minimize unnecessary shutdowns of the whole facility. So this is a completed model, a 2D model of the facility. As you can see here, there are pipe racks going through east-west here. There are compressor shed, and then, so there's pretty large compressors, close to 15 of them in that area. There is a loading rack here, and then there are all these different trains of process. There are some storage areas as well on the top left side. So all that is modeled in 2D, and then this is what it looks like in 3D. You can also see some of the buildings here, and one of the buildings is a control room. As you can see, it's close by, and can be in the line of hazard. And so that's why it's very important to realize what your hazards are and then define what your detection is going to be. The next step is understanding the consequences. So we take all the flammable contours from the consequence model and run them for each piece of equipment. What you're seeing here is a composite contour for the facility based on 20% LFL. The orange, what you see is the LFL, or the lower flammability limit, and the red contours are the UFL, or the upper flammability limit. The reason why you don't see the green or the 20% LFL value is because it engulfs the entire site. However, as I mentioned, this is a composite contour. Each piece of equipment has its own contours that are built in 16 different wind directions. And so that is also considered in the analysis. The reason for the 20% LFL is because that was the set point agreed to during the early stages of defining the philosophy for this site. Thermal contours show the different thermal composite contours, and the 37.5 kilowatt per square meter is generally of interest because that's where your structural steel starts giving up, and so you definitely want to look at either heat detection there as a means of detection over a large swath of area. So this is the analysis, and this is the layout of the detectors. You may think there are a lot of detectors here, but again, I think it just depends on the risk that you are covering. So if it's in a very remote location with no occupancy around, and the philosophy is where you're not initiating any type of major actions, then maybe the number of detectors can be significantly reduced. In this case, the site wanted shutdown of the particular trains based on it, and so that's why redundancy was extremely important, speed of response was extremely important, and coverage was very, very crucial for the site. This slide shows the fire detection or the flame detection. And in flame detection, based on the obstructions, the coverage is going to change. And what we do is the fires are imported, and the fires particularly are directly evaluated against the flame detector coverage or the field of view to determine the actual coverage of the fire and not just of the obstruction. So this is a completed model in 2D, which has your gas detection, flame detection, and your open path detectors as well. There were no toxics on the site, so we did not have any toxic detectors here. You can see there are some open path detectors here, and there are some south of this facility as well that we ended up putting in to make sure that if there is a release going towards the campsite, then it is detected. So again, this is a 3D model of the facility with all the detectors in place. So we talked about consequence. Let's talk a little bit about risk. We follow two approaches. One is, of course, defined by the TR 84007. And in that, there are three main components. It says that detection coverage is important, of course, because you want to make sure that you are able to cover either the scenarios or the area of interest, area or volume of interest. But also, what happens after that? So once you get the signal, is your control system or whatever controller you use, is that adequate for the purpose? Can it take the actions and give you the availability of your fire and gas system? So whether it can take the signal and initiate a shutdown, initiate your deluge, or whatever action you take based on it. And then finally, if all that happens, is that still effective as a mitigation? As you can see here, the example of a propane bullet at normal ambient conditions of 90 degrees Fahrenheit or close to 30 degrees Celsius, 32 degrees Celsius, and 160 psig. If there is a pump supporting or downstream of that, if there is a seal leak from the pump, then it can cause a levy scenario. And in those cases, there is a protection. So there is a fire detector located here, which can initiate a deluge system. Now you can see, based on this chart here, that if a release ignites, there is detection of the fire. But a lot of things have to happen successfully after that to make sure that not only are you keeping the vessel cool to prevent a levy, but also you are mitigating the actual hazard of the fire. So here, there was one fire detector, and we analyzed this case through an event tree approach, which is a risk-based approach. So you look at the ignition probabilities, you see the direction where the fire is going, and then whether it's successful or not, and if it is successful, whether the response is successful or not. And then based on that, you can determine what the final consequence is going to be. The numbers here are suggestive, so please don't use that. This was just a case study. But it is important to understand your probability of detection, but also the probability of your control system preventing that scenario, and then it being effective in its mitigation. Now, this may or may not be feasible for all your scenarios on the site. So you may have to determine which scenarios are of that higher hazard or consequence that you want to cover it with this type of a detailed analysis. The other approach is a QRA or a risk-based siting study approach. Many sites have been doing risk-based siting study for the last decade or more. And you get a lot of valuable information, like the societal or the individual risk results. And those results will help prioritize which detectors you want to place first. And the method of doing that is identifying your high-risk sources and then looking at where, and maybe creating some thresholds, an example threshold value. Again, please don't use these values. These are example values that you can place them in different buckets and say, these are my high-risk sources, and I want to cover them first because I have a limited budget. I don't want to put 100 detectors for my site this year, but I can afford 30 detectors this year, maybe about that much next year, and then rest I can finish it up in the third year. So this can help you prioritize and make sure you get the most value for your detection system. The next topic is scenario coverage research. And let me give you a brief background of why we got here. When we've been doing this work for a decade and probably more, what we were finding is that there was a false sense of security based on placing these detectors in the field. Like any other technology, there are pros and cons of detection technology. And it's very important to understand the limitations of those technologies before you can assume that you have X percentage of coverage. Let's say you have 90% of coverage. But if you don't know the basis of that, then it becomes extremely hard to figure out and have a successful implementation. So some of the key things that we were trying to answer is what happens with different release directions, what happens with fluctuations, what happens with different weather and wind conditions. And so that's why we started doing some research, and we decided to do a series of tests to answer those questions. So we did a total of 74 tests for releases with saturated propane starting from ½ inch going up to 1 inch. We did it in different orientations. So horizontal is the downwind, west and east is the crosswind, vertically up and vertically down. And then we used 14 detectors in a grid pattern located 60 to 200 feet, or about 20 meters to 60, 70 meters or so from the release point. We used 3 different manufacturer products. The first 5 tests were to determine if there is a difference in response times with and without the weather baffles. And this was more from our understanding perspective is, because in general, weather baffles are going to be installed on pretty much anything that's out there within the weather conditions. But without that, is the sensor quicker, and are we getting the responses faster? So this was just our understanding of how the technology behaves. The next 5 tests were to determine the different types of detectors and the response time so we could analyze properly. And then finally, the main set of tests were conducted randomly in different weather conditions, different wind conditions, days, nights, spread out over multiple weeks, and in random conditions, in a random pattern, so that we could analyze it and determine the response characteristics. So for this presentation today, we'll limit ourselves to ½ inch and ¾ inch discussion. We conducted 58 tests total. The detectors were not moved. They were all at 1½ feet, or about ½ meter. So this is the test pad that we have. It's the area of the test pad itself is 80 feet by 80 feet, or about 23 meters by 23 meters. And you can see the detectors in a grid pattern going all the way close to about 200 feet, or about 70 meters. So this is the video of saturated propane being released on our test pad. And as you can see, the gas goes and interacts with the gas sensors out there in the field, and we were logging those values continuously in our historian. The considerations here were the initiating event frequency is, of course, 1 for this scenario. The probability of wind in the direction of release is considered 1 because the winds were steady and in the predominant wind direction as well. And then based on the above considerations, the scenario coverage was calculated for each of the 5 release directions, and then cumulatively for all the 5 directions under different wind conditions. So the results, as you can see, the downwind releases were able to be detected with 1 detector or 2 detectors, but the response times varied significantly based on ½ inch versus ¾ inch releases, and that's expected. The vertical up releases, as you can see, we're not able to detect any with 14 detectors in pretty close vicinity. The crosswind releases going opposite from the release point, we were not able to detect, but the one going towards the east eventually made its way back to the detectors, because initially what you have is the momentum of the jet, and then eventually when the wind takes over, it still ended up at those detector locations, and we were able to record values. And then vertical down, we were seeing a lot of pancake movement that eventually also led us to these detectors. What I've not shown here is some of the alarm timings of how long did it take. I'll be happy to share any of that information if you can send me an email offline, please. But the interesting thing is, if you cumulatively took those 5 different release directions, the overall coverage value comes to about 60%. And it's very important to understand that the limitations of this. The other thing that also needs to be considered is, how does fluctuation take an important role in determining whether your gas actually contacts a sensor for a certain period of time. We were also contracted by NFPA under the Fire Protection Research Foundation to do testing on different types of material with propane, methane, saturated, and vapor to understand the impact of deluge on vapor cloud. We had about 28 detectors, gas detectors, located in the field at different locations, both in the cloud center line and in a fan arrangement 10 feet away in both directions from the cloud center line. So here we were, of course, trying to understand the impact of the deluge on the vapor cloud, but we were also trying to learn the impacts of condensation, what happens after the sensor gets saturated, does it come back to normal pretty quickly, and the characteristics, the response characteristics of that. So as you can see, the deluge just kicked on, and in this case, the gas gets pushed back, and so it gets pushed down and pushed back. But at this high a momentum of 0.3 kilograms per second, the deluge was not considered to be a very effective means of mitigating the hazard or the vapor cloud. But the full report is on the NFPA website, and at the end of the presentation, I'll share a link to that report as well. So we've talked a lot about flammable gas detection throughout this presentation today. Let's take some time to talk about toxic gas detection. Many sites may be using toxics as a raw product, or they may be producing toxic material like ammonia or others. And for those sites, as well as sites neighboring to those, it's very important to have a very robust detection mechanism to ensure that your folks are able to go to safety. So this is an example of a toxic shelter. This is Fortress Protective Building that is at our test site here in Texas. This is also designed as a toxic shelter with an internal toxic SIP room, which has detectors. So we have detectors at the roof air intake, at the inlet, and then scattered throughout this building. To the topic of performance-based gas detection, what triggers someone to go into a toxic shelter? So one is visual, right? So if someone sees that there is a toxic release, they may radio other folks and say, hey, move to shelter. And in many cases, if the leak is small enough where it's not visual, then in those cases, or it's hidden or people are not exactly at that location, then it becomes harder to detect such releases. But if you have unit gas detectors, let's say for ammonia or others, and you ensure that it has a robust evacuation or an alarm mechanism to alert all the personnel around the area and say, hey, move to the toxic shelter, and they move to the toxic shelter. Now the criteria is whether, do they have enough mechanisms to monitor the concentrations at different locations, inside and outside, so they can make an informed decision whether to stay in shelter, whether to evacuate. If they do evacuate, what kind of PPE will they need? If they do want to evacuate, which direction do they want to go out in? So with all that perspective, it becomes a very good case or a problem of performance-based gas detection system. And similar to the inventory that I showed you with the ISA 84 Technical Report 7 approach, a similar inventory can be built for a scenario like that. So let's say here in initiation, and maybe the font is too small, but we can share some of this information. It's also on our SIP document that I'll share a link to in a brief moment. But in this case, let's say there is an ammonia release, and if the release occurs towards the shelter or not, if it does occur towards the shelter, then it's very important that your detection mechanism is adequate. So both your unit detectors as well as your shelter detection gives you that feedback of yeah, I need to shelter and I need to move in this particular direction and wear this PPE to get there. And then based on this action, like any other thing, whether is that effective mitigation or not, that depends on whether you are able to shut down your HVAC system, whether the separate shelter room has all the detection mechanisms and the air quality monitoring, etc., to ensure that people are safe within that shelter. So the thing that I'm trying to enforce here is detection is one piece of the puzzle. It's not the full solution. And it's extremely important to realize the limitations of that, but also work through and understand what your response is going to be based on it. Because without an adequate response, detector is really moot. And so it's crucial to have a full plan developed based on your detection system. And that goes back to that original point that I was making on defining the philosophy, the fire and gas system philosophy, and the response to ensure that you have a safe workplace and you are able to protect your asset. So again, where does fire and gas as a service come in? Just to reiterate what I was saying, understand the hazard, and that can be done scientifically. There are lots of good models out there. You can use that information that you've already developed for your site. You know all the hazards, and then use that to define what your philosophy is. Based on that, place the detectors, and then eventually ensure that your mitigation is effective, whether you're using a fire monitor, deluge, shutdown, or any other means. References that I used for the presentation today are listed here. And for papers that Baker Risk has published, you can request them through our website, bakerrisk.com, and we'll be happy to provide you some of those papers.